is a coin, a corner. And we blow up, and the next blow up is also a corner. Maybe here or here. And so on. So the last part of the bamboo which can be called of length S plus 1 is also a corner, and the next blow up is not a corner. So you blow up the point, you obtain a projective line. The strict transform of the two divisors are in the origin of the card number 1, chart number 1, chart number 2. And we look here. We have an object that is following this wild bamboo. This object may be a vector field, it may be a foliation, it may be a curve, it may be a function. Assuming it's a function. So the function we would like to follow is a function f like that, in two variables. It is a polynomial. You can identify this with a polynomial, with a series. Even if you want, you can identify with a formal series. So you have to write down the polynomial like a sum of this type. What we would like to have? What we want is to approach, because you have only to have an objective to obtain that in other coordinates and after blow-ups, this function is like a monomial times a unit. This is our objective. So what I would like to show to you is that if we are following the function along a wild bamboo, we are in fact approaching the objective in an essential way. So if we encounter finitely remaining wild bamboos, we have already won. This is the idea. Okay. So here I will put coordinates like that at P0. And at P1, I will put coordinates like that, x1, y1. At P2 also, like that, x2, y2. Here, xs, ys. And here, we have x prime, y prime. So, take a criterion. The criterion is if you have only one divisor, try to put it as x equal to 0. So now let us look at the equations. So we know that x equals x1, y1 y equals y1. At the second step, we have that x1 equals x2, y1 equals y2 x2, or x1 equals x2 y2, y1 equals y1. This depends on the fact that you are choosing y2. It depends on the fact that you are in the horizontal or in the vertical tangent that will correspond to the choose of choosing P2. But in general, this is true for any step. So in general, xj equals xj plus 1, yj equals yj plus 1, xj plus 1, or the other possibility. At the final step, we have another situation, is that x prime equals xs and y prime equals ys over xs minus lambda. Actually, this is exactly the key polynomial of Mark. There is no valuation. You can reconstruct the valuation if you want. But here we have this geometrical situation, and it is the same. So now let us use that blue thing to put general situation. So what it happens is that x equals x j aj yj bj xj cj yj dj, and this matrix has the third matrix right. So you can see, and now what is y prime over x prime? So y prime over x prime, in fact, you can do the computations. It is a matricial thing, because each matrix is obtained by the previous matrix. If this is the matrix AJ, you have that AJ plus 1 equals something like that. 1, 1, 1, 0 times AJ, or AJ plus 1 equals 1, 0, 1, 1, AJ. I don't remember if it is AJ or transpose. You can do it. Maybe it's later. So in fact, what you're doing here is that this is something like this. So you can look at this relational function phi. And looking just at this last step, excuse me. This is the last step here. So this rational function phi, it is like something of value 0. So it is more or less like saying that the value of the numerator equals to the value of the denominator. This is done in the last coordinates, but if you do it in the initial coordinates, you have the value of y over d equals to the value of x over p. And this is the relationship with the key polynomials. Since the value lambda is the number lambda chosen in such a way that the value of y prime is bigger, exactly is bigger than c. But for this, it's not necessary to have a variation. So we have this kind of relationship between coordinates. And now our problem is not to follow the Wieser's package. This is called Wieser's package. Including the way you are working with the coordinates. So our objective now is to know what happens with f when we are doing the whole package. So we are looking to f here, and we would like to compare f at the point p s plus 1. So I am going to use this macro. We can go first in order to have an idea. The Newton cloud of F. I remember that F is like that. So why I have drawn these things, this integral net? Because it is important that the exponents of f are integer exponents. And this is precisely the reason because you won. So now we are going to consider lines excuse me, before this, of course, there is a very interesting geometrical object here, which is the curve like that. So this curve exactly arrives here. this curve is also interpreted as a key polynomial for this case.
You mean yp minus lambda x?
YD.
YD.
Minus lambda xp.
Ah, so.
It corresponds
Okay.
to the contact rational function. I call the contact rational function. Now let us consider the value that L0, that is V over V plus U over P equals to 0. And of course, the line LC will be U over V plus U over P equals to C. So, lines like that. Then we can write down F as a sum and C of F LC, where the support of FLC is contained in LC. What means the support? When you are drawing the monomials, you are saying that precisely the monomials are exactly in that line. So now consider FLC. So I would like to write down how is FLC. How is it? I go there. First observation, which is very important, is that the key that appears here is bigger or equal than 2. This is immediately done by the computations, and it corresponds to the geometrical fact that your first blow up is vertical. So let us write FLC. So FLC, the monomials of FLC are quasi homogeneous. But anyway, you can divide something by x, and also you can divide by y. So divide by x as you can.
You should make a picture. Make a picture.
I am going to make a picture. I'm going to make a picture here. I'm going to take a slope, say 3/4. Assume that 1, 2, 3, 1, 2, 3, 4. No, 6, 3, 4. So you can be here. Actually, assume that this is C and this is LC. So there are, in this case, exactly 2 monomials possible. So this one monomial and this one other monomial. The other ones does not exist in this case. But you can divide by x here, and also you can divide by y. So you do a movement like that and like that to adapt in a maximal way your polynomial. So let us divide it by y. And here you have a polynomial q of xy. And what appears in this polynomial q of xy? What appears is that q of 0y is of this type, y power bm, q of x0 is x power tm, maybe a coefficient here. And in fact, q is of the form r of y dxp, where r is homogeneous. Homogeneous of degree n. I am in a small corner of the blackboard, but this is very important. Because what is very important is that n is less or equal than the degree of f divided by d, and d is bigger or equal than 2. So, okay. The degree of f is a bound from this high point. Okay, now we have many things, but we have this way of writing down. Let us write down in another way. Continue here. Q is a homogeneous polynomial, so we can divide all by x over p to the degree of to the degree of r. Well, and what we have is that here we have x p times n r of 5, 1. And R is a polynomial of degree n in one variable. Now try to write down all this in the coordinates x prime, y prime. So if we write down all these in the coordinates x prime, y prime, we obtain that FLC equals to x prime power c. After, remember that y prime is the same thing at 5 plus lambda, which is a unit.
Minus or plus?
Y prime is minus, excuse me. Minus. Lambda. Then you have here something like that. Y prime plus lambda over d. And r of y prime plus lambda 1. Smaller or equal than n. And now we are going to see what happens with this line after all the transformations. What this happens is that, forget for a moment this unit. So I'm going to draw here. In a vertical way. After we multiply maybe by a unit, but the lowest term persists. So this lowest term has a height which is smaller or equal than L, smallest than the degree of F. And in fact, if you choose the smallest C, the initial part of F, all the other parts of F have the same behavior, but came after, like here. So if you are drawing a new Newton polygon, you find that point, and the new Newton polygon is like that. So this value h decreases, and when you restart, that value h is bigger than the new degree of the polynomial, and in this way you obtain finally that the Newton polygon has only one vertex, because this goes to 0. To have only one vertex is easy to understand. It means that your polygon is a monomial times a unit, and it was exactly our objective. Okay, this is just for illustrating how the reduction of singularities works when you are following Puiseux's packages. And in fact, when you work with vector fields in dimension 3, it is essentially the same thing, with, of course, many technical problems, but it is essentially the same thing. Few words about the general Puiseux's packages. So now we assume we have a valuation. This valuation may be, for instance, the valuation associated to a non-oscillating trajectory of a vector field, or this valuation may be a valuation. In general, to do this, it is interesting to have that the valuation has center dimension 0, that is a true point or a closed point in the language of Chins, are more clearly a rational point. More interesting. This means that the residual field is always your ground field. But these are technicalities. So assume that you are working in a point P of your space, and you have your variation, or if you want, your variation ring. and assume that the valuation ring dominates exactly the local ring at the point P. So since our ambient space is always non-singular, the maximal ideal corresponds to the local coordinates at the point P. And we have local coordinates, but we can choose local coordinates in many ways. And we would like to have a particular choosing of local coordinates. We would like to put inside the set of local coordinates a basis for the semi-group, for the group of the valuation. Remember that there is something which is called the rational rank of evaluation, and it is the dimension over the rationals of this group considered as a set module or a Q space, vector space. Okay, so we would like that are self-independent and R is the rational rank of mu. This is not done. You have to work a little bit. And to do that, it is very useful to use the whole Hironaka reduction singularities. And one can say, why to use that for a thing that maybe can be used to do the reduction of singularities? Because we cannot be interested in do the reduction of singularities of objects such that this reduction is not known. Say foliation, say vector field, say other objects. And the reduction of singularities of Hironaka is known. So up to lower, we can assume this. And we can recompose, excuse me, I'm going to change the name. Our coordinates into parts. Independent coordinates, I mean coordinates with independent values, and the other ones that are necessarily dependent coordinates. So if you choose now one of the dependent coordinates, say y1, what arises is that the value of y1 equals to p1 over d, the value of x1 plus p r over d, the value of xr. So this means that the value of phi, which is exactly y over d divided by x1, p1, x2, p2, xr, pr, has value 0. Don't ask me, please, Bernard, about the fact that maybe one of these coefficients is negative.
I was going to ask.
Eh?
I was going to ask.
This is not a problem. No problem. You do a little bit more going up, no problem. Okay. So we have 5, and now because of our assumptions, yeah, we can find a unique coefficient in the ground field such that we have positive value. So this means that if in one point of the world, of the bidirectional world, phi minus lambda is a coordinate, it is close to the center of the valuation. So finally, you have here one algebraic variety, very easy to understand. And you can do the reduction of singularities of this algebraic variety by blowing up just things of k-dimension 2, which are very easy, very combinatorial reductions. And the last step can be drawn exactly as here. And in the last step, you can say that one of the coordinates is exactly 5 minus lambda. The other coordinates, x prime, are a combinatorial combination of the x times a unit. And this is an organized way to see what you can do by growing up in say, tonic packets. Maybe it is also a way of understanding the next conference. But the arguments you can do here in higher dimension work more or less like the thing I have already done. No difference. No difference. And this is a way you can do the local uniformization, for instance, of functions. It is true that you are not doing that because you need to use the relation singularities of Gironaka. This is a small detail. So I am changing these observations against the whole reduction of singularities of vector fields in dimension 3. So because of these observations, I know how to do the reduction of singularities of vector fields in dimension 3 when this reduction is possible. Because tomorrow we will see that it is not always possible. But this is for tomorrow. So now we start another talk. So, one observation. We need ramifications. To get elementary singularities. It is necessary, but tomorrow I will show to you that it is necessary. And so this part of technical things I skip. There are several papers where you can write the details. I am going to put them in the cloud, but I'm not sure to ask to do a copy because maybe the paper will be too big. So what is an elementary singularity of a vector field in dimension 3? assume that you have a vector field in dimension 3 that has a singularity at the origin, and you say that the singularity is elementary when the linear part is non-nilpotent. Elementary part is non-nilpotent. So you have one non-zero eigenvalue at least. It is also true for the real case and for the complex case. So, assume we arrive here. And now what is one of the applications of that reduction of singularities? So I would like to explain about one application. The application is one application we have used is in the real case to distinguish the two types of Galois packages. And then I have more or less 10 minutes. I will try to speak about how to use the reduction of singularities in order to prove that the Galois packages of a non-oscillating trajectory of a vector field are of type separated or are of type dancing. So remember, we have a trajectory gamma that is transcendent plus non-oscillatory. So the Galois package of gamma is the set of all trajectories that share the same iterated tangents with gamma, which are very close to gamma. All of them are necessarily the same thing. Non-oscillatory issue. Transcendent is not so sure. So assume that we look only at transcendent objects. So we say that it is separated if and only if, I remember, there exists a projection of the ambient space to R2 such that, for each gamma and tilde, such that the image of gamma and gamma tilde do not cut itself.
R2.
No, the origin is not in the image.
R2.
R2, excuse me. Thank you. And it is a dancing if and only if up to rho there is a situation like the following one. We have a device we have a forward curve which is non-singular, and each two trajectories turn around. How to say that you turn around in that situation? It is not so difficult. You can take the theta constant and you take 2 points here and a vector. And this vector, you can see it turns. He turns. If it turns, when C goes to 0, and this means turning around. Of course, if you turn around, it's not possible to be separated. It is not clear that one Gauss package is of one type or of the other type. It is not clear. But what is clear is that the situation is true, is stable by blow-up. Blowing up. So I mean, if you have one package one type, you blow up, you obtain one package of the same type. It is true that in the second definition, I say up to blow up, but you can do the definition without saying that. It's just for being clear. So finally, we can blow up along the valuation given by the trajectory. The valuation given by the trajectory is not necessarily a valuation that follows a formal curve. So in some sense, it is a quite general valuation. And you have to work with a general valuation and the vector field. So we invoke this axiom and we obtain a point which is elementary. And now when you are in an elementary point, what do you have to do? Because the work in an elementary point is not immediately done. You have to do the work. So let us arrive to an elementary point just for proving the above dichotomy.
Why is it called Galois?
Because it has a certain analogy with the idea of ambiguity. So you have two trajectories sharing the same identical tangent. You cannot say what trajectory are you touching. And to select one particular trajectory is an analogous operation of selecting one particular root of a polynomial. This is the reason. So you assume now that gamma is elementary. Vector field in R is 0. And we have our trajectory gamma. There is an eigenvalue associated to gamma, in fact, because gamma has tangent, and the tangent of gamma really touches one eigenvalue of the linear part. This is not easy not difficult to admit. So there is an eigenvalue associated to gamma. And this eigenvalue, this direction, may be strong or weak. So, if A value. So essentially, we are inside the so-called stable or unstable from the dynamical system theory, and really you see that the gamma is either analytic or in fact separated. Because of the fact that in this case you can more or less explain how is gamma by a triangular equation. So you can say that there is a very strong eigenvalue here that goes essentially like that. It is not necessarily isolated, but it is separated. So there are other cases. There is another case such that the spec of the linear part has two zeros and one thing which is non-zero. This means that you have only one non-zero eigenvalue in the linear part and two eigenvalues that are zero. In this case, and you assume that gamma corresponds to that zero eigenvalues. In that case, there is something which is called the central variety. So the central variety is a variety which is not necessarily analytic, it is a C-infinite variety, but it is invariant. This is classical theory. It is invariant. Here we have the strong direction, maybe like that, it's not important. And what we are saying is that gamma, I can change the color, is that gamma is like that. Gamma is flat with this central variety. So you go also to the classical differential equations, and in this situation they say that there is one and only one accompanying curve of gamma inside the variety, such that the distance, parameterized distance, is very, very small. It's exponentially small. And in fact, in this situation, the dynamics produces a kind of lamps like in a mushroom, which are not exactly analytic, not analytic at all. But using that, you can see pair. Because if you are in the same lamp, you see pair predicting like that. If you are in another lamp, you see pair predicting like that. So in that case, you can see pair. The package is separated with another negative. And finally, the other case is when in fact gamma is closer to the central variety. So the central variety corresponds to the only one zero eigenvalue, and this is not this is stable or unstable or part of the two. And here we have the central variety. So the central variety is a C infinity curve. Excuse me, it's a CK curve for any curve, for any case, it's not simple. Because it is not unique. And gamma is like that. But this central variety also is a geometric realization of a formal curve. Asymptotically given by a formal curve. And that formal curve, of course, is necessarily invariant. So, in this situation, you are blowing along a formal curve. And when you are blowing along a formal curve, you can take formal coordinates and still to blow up. And when you blow up, following gamma hat, which has the same integrated tangents as the trajectory, you can put your vector field still in a more convenient way. And the more convenient way is more like that. Here there are something that is not interesting. Say A. These are linear facts. And you can imagine that your curve is the vertical curve. So now you look at that linear vector fields only in variables x and y. And it depends if all of them are radial, you are separated. If some of them is like that, is turning, you are not separated and you obtain exactly the dancing property. It is a little bit more complicated, but you have exactly the conditions in the notes that I have said, or in the course of Fernando Sanz. So in this way, we can at least...
What do you mean, fields?
Fields Institute. Fields Institute in Toronto. It is in... I don't know. So this is at least one application. Of course, there are many possible applications, very interesting also. For instance, there is an application that I like very much, and you can try also to prove. Imagine that you have a vector field which has, in dimension 3, and which has an isolated singularity. So, is there, up to change the sign, huh? Is there at least one trajectory arriving to the origin? Because in dimension 2, that's not true, because you have this kind of centers in dimension 2. And here you don't find trajectories arriving to the origin. But in dimension 3, any matrix has at least one real eigenvalue. And this is what is behind that property that has been proved by Marco Brunella. And the way he proved that property is also by evoking results of reduction of singularities like that. But he needs that the result is more or less not necessarily global, but not like exactly like that. Okay, proceed to move.
Is there any questions?
I would like to make a comment that the name Puiseux package is very well chosen because it means 84 paper algebraic functions. I think Puiseux shows, he follows Newton's method, but he stops by a change of coordinate every time he sees a binomial plus something of higher weight. So it's exactly following the Puiseux package.
Any other questions or comments? Thank you very much. 5 minutes.